or something like this. And you move from ESOC to ESAC to ESTEC. So Larry works on several missions, start with ENVISAT. He worked on Herschel. We collaborate actually on the detection of water vapor on Ceres within the team. And he worked since the beginning in Rosetta, the flight dynamics, if I am correct. And he was responsible of a team looking for Philae lander, especially when we lose somewhere on the surface. So this is why he is expert and he provided these wonderful images that allow the reconstruction of a trajectory of Philae. So I leave the word to Larry to present the results.
Thank you very much, Sonia, for those nice words. I'm going to remove my video now so that we focus on the presentation. So, okay, and then. So my talk today is about the Philae lander and a Nature paper that was, let me just try to see if I can get the, there. A Nature paper published at the end of October. In fact, published around Halloween, primarily because of an image which we obtained of the location where Philae landed, which looked like a skull. So it had a Halloween sort of feeling. But this paper was published in Nature, and I'm going to present the results of this paper in this talk. So it's linked to the Rosetta mission, of course. Everybody knows Rosetta. It was launched in 2004. Took 10 years to arrive to the comets, to this comet, in fact, 67P, Churyumov-Gerasimenko, an object which effectively is the size of about 4 kilometers by 2.5 kilometers in width. It's a bilobe object. It has 2 parts which effectively have joined during the cometary formation, and it's of course it's a mix of dirt and well, let's say carbon, dust, and ice, and therefore it's very black, a black surface, primarily driven by the carbon. And the mass of this, it's about 10 billion tons. Its density is about half the density of seawater, so it would float half in and out of the ocean. Gravity is about 100,000 times less than the gravity of the Earth. So Philae lander, for example, which weighs 100 kilograms here on the Earth, would weigh 1 gram on the comet. And its porosity, which I think is very important, in particular linked to our paper, is about 75 to 85%. So really, it has a lot of, I don't want to say empty space, but indeed it's highly porous. So landing on the comet, when we arrived, we mapped the surface and we released Philae lander. Now the Philae lander was stored on the back surface of Rosetta during the full long journey. We did a campaign to find a landing site, and then we released it. And this is a picture of me when I was much younger, when Philae was being constructed in ESTEC. But it's very much the size of about a washing machine, any washing machine in the kitchen. So we released Philae on November 12, 2014. It drifted down to landing about 7 hours later. And when it touched down, the 2 harpoons, which were supposed to release and shoot into the surface of the comet, well, they failed. And a little thruster, which was there at the top, also failed. So effectively, there was no way that Philae could actually stay on the surface, and as a result, it bounced. And so what we have from the surface of this comet, in particular when it comes to Philae, are the marks left by Philae on the surface. You can, when we look at the first touchdown, where it's first touchdown after this 7-hour trip, we see the marks of the 3 marks from the feet of Philae in this image here. When you look at the Philae then traveled across the surface, so it bounced. It took 2 hours to arrive to its final location number TD3, touchdown 3. So it drifted across the surface. It had a collision point. It collided against the edge of the Hatton Head crater and was actually just touched with 1 foot and was pushed inwards again. And it made touchdown, what we call second touchdown 2 point, number 2, and then it bounced 1 last time for about 30 meters to land on touchdown number 3. Now touchdown number 2, second touchdown point, it was not known where this location was. It's somewhere in this region here, in the Abydos region. It's this region, when you look, if you look inside of it is here, you see it's very much a boulder strewn region with cliffs and boulders effectively up to 10 meters in size. And somewhere here, we believe Philae actually touched down in the second touchdown point. And what's more, we also learned from one of the scientific publications from the magnetometer boom, which is a ROMAP boom. It sticks out the back of Philae. It has a Faraday cup with magnetometer inside, and it was taking magnetic measurements. And we know when it arrived to the touchdown 2 point, it actually penetrated the surface of the comet. It penetrated the dust layer and was covered with dust. And this was confirmed by the instrument team. They lost all data from the sensor. Basically, the only way it could lose this data was if it was covered in dust. It was otherwise working perfectly. And so we had information, therefore, that this was a location that had been penetrated by Philae somehow by the boom. Now, Philae continued 30 meters more after touchdown 2 to the final location, touchdown 3. And touchdown 3, of course, located in a very similar region, the same region, but 30 meters from touchdown 2. And so we had to look for it. And so we had information, of course, where the final location was. We knew that Philae was on its side. It had images taken. It tried to hammer into the surface. It tried to, well, of course, it did a lot of measurements, including the radar instrument Concert, to measure the interior. So we had information of its location, more or less, but we didn't know where it was. And so we kicked off a search campaign. Okay, we assumed that the guys that you see on the screen here from Star Wars, that they did not take Philae, but that it was still located there. And so we kicked off a search campaign in March 2016, about 6 months before we actually finished with Philae. And we finished with the Rosetta mission to try to find the location where Philae was on the surface. And I led this search campaign. So it was a rather large group of scientists and engineers to try to image Philae on the surface. And so Philae, in the end, is located in this image that you see here. Philae is located in this image. It was the last successful image we could take of this region before the end of the mission. And so if we zoom in here and we overexpose, then you see Philae located in the corner underneath the cliff. And in fact, the touchdown 2 location, which I'm going to talk about now, is located here. It's the location which Philae touched down and then floated one last time over to where you see it in the corner. This is Philae here with a nice animation. So when we found Philae on the surface, I want to explain something which I noticed during the lander search campaign. Clearly, we've seen there is exposed ice on the surface of the comet. It's very much covered in dust, but in certain locations, you might find that ice is being exposed, like on cliffs, for example. And in this GIF image, I think is quite nice because you can really see how dark the comet is. It's a very low albedo, but that in certain locations, you do see ice that has been exposed. And indeed, Sonia is very much an expert on studying the ice that is exposed on this comet. But you can see the bright glimmering regions which represent ice. And when we were searching for Philae, Philae itself had a reflectance very similar to the surface ice, but it was very small. And so we were looking for bright patches, always with the idea that the sun was reflecting from the solar panels. And so while we were looking for Philae, I noticed something which in the images which struck me. And it was that Philae, which is located underneath this cliff region here, it's in the darkness. I noticed this image here of 2 boulders which seem to have let's say a flat area. It's like somebody had actually cut through the edge of the boulder. And this image for me struck me. It was 2 weeks before, or well, 1 week before we found Philae in the end. But I found it very strange just because of the way the ice was. And so when we found Philae, then I kicked off a small search campaign to try to see if I could locate this icy region with different viewpoints. And I stopped because we had Rosetta end of mission and I stopped searching. But effectively, this image of the ice exposed always stayed with me. A number of years later, when Rosetta was finished at the end of September 2016, and then we had a post-operations phase. And in 2019, the science working team set up a group, which we call the Seven Dwarfs, in fact. It was a group of 7, and then it was expanded to much more, to 5 more, including myself, to try to create one single trajectory. Because when Philae had landed, there was 6 different trajectories existing from the lander team. And so we were asked to create one single trajectory, do our best to consolidate it. And we came up with this one trajectory here, where you see touchdown 1, the collision, touchdown 2, and touchdown 3. And if we focus now on touchdown 2, as part of the trajectory, this was what we believe to be the most consolidated trajectory, one single trajectory. Then we started discussing, well, where was touchdown 2 point? And so you know where the location is. You see the yellow spot here, and that corresponds to Philae hidden under the cliff. We know where touchdown 3 is. You know the distance, more or less. You know it's 30 meters because you know the time it took to fly across from touchdown 2. And so you can create effectively an error cone going out, and you can actually, which overlaps this hill-like region here. So somewhere in here, which is many meters across, we believed touchdown 2 was located. Now, Philipp Heinisch from the Technical University of Braunschweig published a paper in 2019 on the basis that he believed touchdown 2 was located in this region here. And when the trajectory group came up with this location, I stepped in and I said, well, hang on. In September 2016, just before we found Philae, I noticed this strange icy feature, which is located here. I said, my belief is that I think this is Philae, where Philae located, where this is the location where Philae sliced through the ice. We did some further analysis in the trajectory group, and certainly this location was better than the one proposed by Philipp. And so I kicked off an analysis to try to see if we could prove that Philae had landed here. The first thing to do was try to see if what is this water ice? Well, is this ice that's in the crevice? It looks much brighter than everything else around it. It's about 5 to 6 times brighter. We believe it's ice, but of course you have to prove it. And this is where we looked for other images of this location to see if we could find this bright ice feature. And we found some images in June 2016, where I'm going to, you're seeing it, this image here, it's bright in this image, but I'll show you a different viewpoint. This here was the bright ice location, but it's this, you see the full comet, and so it's a WAC image. It's the OSIRIS wide angle view. It's a low resolution, and so we zoom in, and then we actually put on the NAC image. So this is the WAC. NAC, you see a higher resolution, and you start seeing the bright spot in the yellow. So we zoom in here, and you can see that this is the ice exposed by the sun, reflected by the sun, visible in this image. And so what struck us when we zoom out, and I go to here, okay, and then I remove, let's say, just remove the WAC, and I just then remove the contrast and the brightness in the image, such that this viewpoint is purely of the bright areas. And then even when I switch off the light, if your computer is good enough, you will find that this spot is the ice that was visible here was brighter than everything on the top surface of the comet. It was extremely bright. And of course, the question is then how, if it's so bright, clearly it's unprocessed. It's quite pure, if you want to say it like that. And so this was where I asked for Sonia to get involved. It was very much appreciated, her role in all of this. And so what was done was that we had the albedo of the ice was measured. Sonia and her colleague, I just can't remember the name right now, but they did an analysis of this location of the bright ice. We had the benefit that when this viewpoint was there, we had multiple wavelengths of the OSIRIS data. So the many filters of OSIRIS They were able to do a multi-filter analysis. They were able to find that this location, the albedo was 5 to 6 times brighter than the dust-covered region. It covered an area of 3.5 square meters, which is quite a lot. And they derived the water ice abundance basically from the observed reflectance. You correct for illumination conditions and phase function based on the dark terrain and the water ice. And effectively, you then work out that the water ice abundance value, about 46 to 47%, was measured. And this leads to local dust ice volume ratio of 1.15:1, which is extraordinary. But basically, when you take into account bulk density, then it's about 2.3:1. Now, what does this mean? Okay, what it means is that this brightness, this ratio of water ice to the dust, is the average that's been found around the comet was that this ratio was greater than 3:1, so 3 times more dust than ice. And for us, we found a value which is much lower, 2.3:1. And in fact, this low ratio of dust with respect to ice has been found also for newly exposed ice that you find at the bottom of cliff regions where a cliff has broken and you see an outburst. You see newly exposed ice, and so this newly exposed ice, or this ice which we were taking an image of, this image was taken 22 months after Philae had actually penetrated the surface. So clearly it was in a region which was quite protected, because normally we've seen that ice, when it's exposed and there's an outburst, then gradually over time it loses this reflectance, it loses this high abundance, and it's primarily because maybe it's covered with the dust, etc. We also looked at Virtus, I did an analysis to try to, with a shape model, to try to work out when did this region pass through the Virtus field of view, in particular on the same day when it was bright. And we did, in fact, were able to repeat that we could get a science result also from Virtus, the infrared and imaging instrument on Rosetta, which was able to confirm the OSIRIS finding. They were able to confirm that this was a water ice rich spot, and therefore, with 2 different instruments on Rosetta, we had confirmation that we had water ice in this crevice. Okay, so now you know it's water ice. Great, but how do you know it was Philae that made this, that exposed it? Well, the next thing was to try to do a full image analysis of pre and post landing. Pre-landing, you want to find a location where Philae touched down and compare with it post-landing. So do you see changes? And so we got 2 images here, which are taken at the exact same distance from the comet. One in the 22nd of October, a few weeks before the landing, and one, of course, a number of years later in May 2016. It's the same distance. The phase angle is quite similar. The sun illumination is slightly different. And so, but of course, and you're seeing different areas. But what are we looking at? We're looking at that inside this region here, which is the same region on both sides. The touchdown 2 location is located here. And so we want to try to find it in this image. It's just very difficult because of resolution. And it's also very difficult because this region here is very boulder strewn. It's a lot of boulders. It's very difficult to find something when you look from different directions. And I'll explain what I mean. This here is the image I showed earlier on. You can see the ice in the middle. Now, if we look from a different viewpoint, this here is that location, but you're no longer seeing the ice because, of course, it's in a crevice. It's closed now. You can't see it, and because of sun illumination. If you look from here, this is looking from above. Where is it in this image? From here, you're looking from another direction, somewhere here, and from here. Each of these has these same 2 boulders in the image, but because of the direction from which we're looking at, it's very difficult to find them. And so I use shape models, and basically with these shape models, 2 different types. When you use the shape models, you can, of course, superimpose the image and identify the region in the shape model. At this point, you can then do rotations. You can mark the location, as you see here with colors, and effectively from this, you can change the shape, the orientation of the shape model, whether it's a local DTM or even a more, let's say, a larger, a poorer resolution. But effectively, you can then find the touchdown 2 location, the 2 boulders from any direction you look. And so this is what you see here. So this is the view we know, the slice in the middle. And then finally, from using the shape models, you can identify that this is the front boulder, this is the back boulder. You can identify here, this is the front one here, the back one here, here as well, the front, the back. So basically, from whatever direction you look, you can find it. And then during all of this analysis, I found hidden in the darkness that when you look from one direction, in particular, we found that the front boulder, well, the bottom boulder, let's put it this way, looked like a skull face, and the top one is called a skull, had a like a hat, and the right eye, in fact, was made by Philae when it came out. But basically, we call this area then the skull top ridge, and this is the skull face. And so we ended up finding this really strange looking image. So now we're able to locate the location that, irrespective of whichever direction we look. We have lots of images, and so we can just now try to do our geomorphological analysis. You can compare, find the same regions on any of these images, and then when you've got these same regions, at this point you start looking in the regions for changes. You find boulders that are all of the same size, structures that have the same shape, and so you can really do a full analysis to identify the same features, and you can look pre-landing and post-landing, and now you know these features and this location in detail. And when you do that, then these 2 locations, pre-landing and post-landing, you zoom in, and at this point, you can do a comparison. And you find that the best way to compare is that you see the what looks like a guitar sort of shaped here, the blue sort of feature here, and you see it's also in this one. This is the same location, it's just a different view. In the corner here with the arrow, you see Philae. So this is a post-landing image. That's not there in the pre-landing. And then if you, inside this yellow rectangle, you see a blue sort of feature, which is like what I call, it's a ridge region, and then you got the yellow. And when you look in the yellow in detail, then you can identify similarities. You really look for those boulders that are the same. And you find that the pre-landing and the post-landing, you see the same boulders. But when you do the differences, you actually find that there's certain things that have changed. For example, on the front boulder, there's a very clear edge on the front boulder in pre-landing. In post-landing, the edge is gone. It's a very diffuse sort of feature. We find that it's a very clear line from the shadow of the sun along it. It's a very clear line, but when we look here, we suddenly see something has changed, that there's a change. So we see lots of changes. And so this allowed me to then reconstruct. We identify all the changes, and then we reconstruct how did Philae come through this region. And so we have Philae. This is just an animated view of Philae. Comes down from when it was falling, crossing the surface, it came down and slid down the front of the boat, leaving a long mark along the edge. At this point, it changed direction. So this is a different view of the same thing. So now it comes down and falls behind the boulder. Okay. At this point, okay, it's come behind this boulder. It passed through the 2 boulders. So these 2 boulders are they're end on end, and they're full of dust. The crevice is full of dust. So what I mean by that is that one of the boulders is much higher than the other. And so like when it snows, where you have what's called a drift, you effectively have one side has got a lot of dust up against the edge, and it fills the crevice. And we know that Philae came through this crevice and it rotated like a windmill. And when it rotated like a windmill, it also exposed the ice on both sides, which is what you see here. You see ice on the right, you see ice on the left. And it also removed a lot of the dust. So this is it coming through the crevice. When it got through the crevice, at the end, the crevice narrows. It gets narrower. And so Philae was pushed, basically couldn't fit through anymore, and it actually got stuck and pushed forward. And when it pushed forward, that's where we see this. We just take this image of the ice that I showed before. You see this location. And when you compare this region here, you actually find a direct mapping with the front face of Philae. we're able to match the tower, which is something which sticks above the surface of Philae. We find a hole where it actually slotted in. And so we find that Philae itself has left its mark on the surface of the ice, like this. So effectively, you're able to work it all out that Philae has actually compressed this region. It moved forward and compressed. Effectively, it's at the end of the crevice here, it moved forward and compressed the ice, leaving its mark in the surface. And when you measure the compressed region, the area itself, we're looking at an angled view, but basically you can work it out that compressed area is greater than 0.22 meters squared. And this is very important when you measure the compressive strength. From a structural perspective, you're dealing with two boulders with a crevice in the middle, which measures the width of the crevice is about 1 to 1.5 meters. The height of the front boulder, so this person here is about 1.6 meters in height. The ice that's been exposed, this strange ice that you see here, it's 2 meters in height. It's a huge structure that's in the ice, and this is just there to give you scale. So the height of this boulder on the left-hand side is 4 meters. So next time you're looking for ice, look at the wall of your office and work out what 2 meters is. That's how much ice was there. Philae compressed the ice and then lifted up. It started coming out of the crevice. It touched the front of the crevice and then moved forward. At this point, it was pushed downwards and left its face, left its mark, creating the right eye of the skull. And when we look at the dimensions, we find the dimensions of Philae match with the dimensions of the compression. Basically, this confirms that Philae made it. Good. That's what happened with Philae passed through. But now we're more interested in working out this impression made by Philae in the surface, its compression. Can we work out what was the strength of this ice? But to understand how much it's compressed, you want to understand also, well, this depth that is measured, that you're measuring, has sublimated, has a lot of ice sublimated from this during the 20 months after Philae passed through. And so what I did at this point was to do an engineering analysis using what's called a horizon mask to figure out how much sun exposed the ice. And so to do this, you see Philae, you see the touchdown 2-point look at it here, you see the bright ice. I take a horizon mask, which is this one. The red is the sun, how the sun passes through the region. Each circle corresponds to, okay, imagine this, the center of the circle is fully on top of the crevice region. And you are looking, in this image, you're looking straight down. You are 90 degrees above this location. This circle here, the deeper circle. So each circle represents 10 degrees off vertical. So effectively you're looking 10 degrees down. This is 80 degrees. This is 70, this is 60 degrees, effectively from where you're looking. So you're effectively trying to, standing on this crevice, you're able to determine where is the horizon, where is the blocking region, like the cliff region here is clearly the sun has to come over here in order to expose the ice, similarly over here. And so you're able to work out, you begin to work out where is the edge. You can see the edge here of anything that would block the view of the sun. You then can work out then the crevice itself and how much visibility of the sun did it see. So you're able to work out with all the images that you find where it's illuminated and where it's not, you can actually create a horizon mask, effectively a shape of a structure of how this must be in order for the sun to get in. And when you pass the sun, you work it all out for different time ranges, you can conclude that I estimated that the sun effectively illuminated the region for a certain number of hours, especially the inside the crevice. This crevice is 2 meters deep, or 2.3 meters deep. So you're trying to see when did the sun get inside? And so you can work out with a basic sublimation model, because there's no need to go any further, that in principle, just with a basic model that you would find that the sun would have led to sublimation of 34 centimeters on the left hand side, 12 on the right, nearly, let's say, half a meter. But we don't see it. We don't see in the physical images this sublimation. Why is that? Because the distance between the base of Philae and the top of Philae measures 1 meter. The distance of the crevice, the width of the crevice where Philae made its compression is 1 meter, effectively 1 meter as well. So basically very little sublimation is taking place. In other words, this location has seen very little sun. If we want to now measure the depth of the compression made by Philae, let's say here's the view that we all know. Let's look into the crevice sideways. When you look in sideways, this is the image where Philae, if you overexpose, is hidden in the shadows. If you look in sideways, you find that the depth that Philae actually compressed the ice is 25 centimeters. Perfect. We know the area that is compressed now. We know how deep it's compressed, but we're missing some important information to work out its strength. You need to know how long did the compression take and how much energy was lost. And this is where we had, let's say, the most key, let's say the key important input to all of this, which was from the ROMAP boom. So before I mentioned that the boom sticks out from the back of Philae, and it has a little magnetometer stick here. And we also know that this boom penetrated dust, penetrated the area, the ice, when it passed through this location. But it also has another feature, unexpected. This was just a magnetometer boom, but what they did not realize when they launched this satellite and launched Philae, they didn't realize that this also can act like an accelerometer. In fact, it can tell you the rotation and orientation of Philae. Why? Because on Rosetta, you have a magnetometer, which is exactly the same as the magnetometer on Philae. And so the comet is not magnetic. And so you can, the data measured by ROMAP should be the same as the data you get on Rosetta. And so if you do a diff, effectively you find that there is differences between them. And the differences could be explained only by the fact that Philae was rotating and was bumping into things. And this was one key result. They were able to work out orientation and attitude just by the magnetic data from ROMAP. But something else was important. And that is that the boom, which sticks out the back, is connected by springs. So if I go back to here, if you shake Philae, you lift it up and down like this, up and down, the boom will move up and down. Okay, so like a accelerometer, effectively, you can actually measure the change in the attitude of Philae, at least in this case. And so these spikes, which you see here, match with when the boom moves. And so we were able to, when we did the analysis, we were able to link these spikes and the specific time at which the Philae actually made the compression. We were able to link it to the data in ROMAP. And we were able to confirm that this duration of the compression was 3 seconds. And as a result, we've got the minimum area, which is about, it's greater than 0.22 square meters. The depth of the impression is 25 centimeters. We work out, we know how much energy is being lost because we have all of this information calculated from using the ROMAP data, and you work out as losing 0.6, let's say, joules just in the compression stage. You can work out the stress that's created by this using comparative compressive strength. The area and the depth gives you the minimum volume that must be displaced, and as a result, we were able to work out that the compressive strength of the ice that was made that was compressed by Philae is less than 12 Pascal. And we also can state that this compressive strength is for primitive ice. And why do I say that? If I go back for a second and show you this image here, which shows the depth that you see here. This depth, 25 centimeters, we know it hasn't changed. It has been very little sublimation, very little sun illumination on this location. We know that. Secondly, we know that this depth, this compression was made when Philae compressed it. And it compressed it when it passed through the crevice. And so before it passed through the crevice, this is one single boulder that has not been exposed to the sun. Its internal properties remains the same as when the interior of the boulder was created, which is approximately 4.5 billion years ago at the cometary, the time of the comet's formation. And so the ice that we're dealing with, that's being compressed, was compressed at the time the Philae passed through. We can work out that the ice of 4.5 billion years old, time of the formation of the solar system, has a compression of less than 12 Pascal. In other words, less than 12 Pascal is softer than the foam that you have on top of your cappuccino. So next time you're drinking a cappuccino, you have your nice foam on top. 12 Pascal is softer than this. It's softer than the foam that you find on the seashore. When you're walking on the sea and you see the bit of foam, if you stand in it, then you will see it's softer than this. Finally, to wrap up the presentation, porosity measurements. So there was, before our paper, there was 3 independent porosity estimations made for the comet. 2 of them were based on, one was an instrument on Philae, the concert radar, was on Rosetta and Philae. One was from the radio science instrument, and then there was a modeled result. Now, the concert radar is a very interesting one because you have an antenna on Philae and you have an antenna on Rosetta, and they communicate. And so this radio frequency, this telecommunication signal, is being sent from Rosetta or from Philae, let's say, for example. So when you have a direct line, Rosetta is above the horizon, they talk to each other. But when Rosetta flies below the horizon, the signal still passes through the comet. And the propagation delay, the time it takes, that slows it down because of the internal structure of the comet. This is propagation delay. This tells you information about the internal structure of the comet. And from this, they were able to work out that the porosity is between 65 to 85%. For our data, we applied a mathematical model to look at, take into account compression that was made, but also determine how much, let's say, the volume filling factor, which is the opposite to the porosity. So if the porosity is 75%, the volume filling factor is 25%. So how much is it filled, taking into account, that we have such a low compressive strength. And we applied a model which was also applied for concert, got similar results, where you were dealing with an internal structure, which is basically a sub-micron size solid grains contained in large units. Basically, it's just pebbles in this case, which again are clustered together to make up the boulder. So it's a hierarchical arrangement of building blocks. And you apply this packing approach with our mathematical model. We found similar results as with concert. And so we worked out that with such an approach, with basic mathematics effectively, we drive a volume filling factor of about 25%. It's equivalent to let's say 68 to 82% porosity, very much in line with what concert has shown. But also, the concert results, because it passes through the full, let's say the head of the comet, this was a scientific paper published, they found that the comet is homogeneous anywhere or everywhere, depends how you use the wording, anywhere in its interior to all size scales down to about 1 meter. In other words, below 1 meter, you cannot tell anything, for concert, but anything above a meter scale, you should have similar porosity. And this is when you look at our boulders, where the front boulder is measuring about 5 meters long, 2.5 meters wide, it's 4 meters tall. Effectively, we're dealing with something which is much greater than this 1 meter scale. And so therefore, our finding implies that, and it shouldn't be surprising really, that the boulders represent the overall state of the comet's interior when it formed some 4.5 billion years ago. Basically, the boulders used to belong to the comet. And this is realistic because you're dealing with thermophysical, let's say, changes on the surface. You're dealing with dust coverage, which is gradually cracking over time, the sublimation of the ices and the gases underneath, which especially when you're dealing with cliff-like regions, breaks apart. And when it breaks, then pieces fall off or are exploded out. And these pieces can be the size of boulders, which used to belong to the interior of the comet, but now are flown and placed on other locations. So we're just confirming, indeed, that the boulders used to belong to the interior of the comet. And so to wrap up, what we've done in this Nature paper, we've measured the compressive strength of primitive ice originating from the formation of the solar system. Our porosity findings imply that the boulders represent also the overall state of the comet's interior, which is fine. I think it makes sense. Philae was, this was unexpected. Philae was supposed to land in one location. In fact, it was going to land on a location which was packed with dust. I would wonder, I would say meters of dust. I wonder whether you could actually get anywhere to the ice. It was intended to land and then penetrate with a drill through the surface to get access to the ice. But we know from this location where it landed the first time that it was covered. We revisited that location at the end of the mission and found that the touchdown one point, which you saw 3 footprints before, they were no longer there. They were actually covered by dust. And so I'm not entirely convinced that it would have got much amazing access to ice from where it was supposed to land. But it did. It got access to it at least touchdown 2 point. And in fact, it actually got signs from 3 locations on the comet. So it's the best unplanned comet hopper experiment ever. It's clear that if you want to access primitive ice or ice in any sort of nature, then it's the best place is to go to unexposed regions or boulder fields to access it, which is never a good idea because, of course, you're dealing with something where you have less sunlight. So if you have solar panels, you will not be able to charge batteries. But also, it's more dangerous because you're dealing with boulders. So it's thankfully Philae, when the word crash landed, was the best way. It actually bounced, and it was the best thing that could actually have happened to the mission. Last point, well, we found the ice was located directly below a fluffy dust layer, which, depending on the location, can cover up to 1 meter in height. And so there's a lot of dust in that region. We were just lucky to, we compressed it quite easily. And certainly, if you want to land in a location, get access to the ice, well, land on a boulder, compress the dust, and then just drill down, and you get to ice very quickly. And that is the end of my talk.